Well, good afternoon, everyone, and I realise for some of you it may not be afternoon, depending on where you are around the globe. My name is Sue Pigden, and on behalf of Noreen Crucial at the Bushfire CRC, we warmly welcome you to what is now the fourth of our webinar presentations in this series. The webinars conducted by our leading Bushfire CRC researchers provide opportunities for not only knowledge sharing, but more particularly supporting the adoption of new research among AFAC member agencies. Today we will be hearing from extreme fire weather forecaster Dr Jeff Kepert, presenting on fire and weather understanding the extremes. Dr Kepert leads the High Impact Weather Research Team at the Centre for Australian Weather and Climate Research, a partnership between the Bureau of Meteorology and CSIRO. The Centre undertakes research to improve scientific understanding of and the ability to forecast Australia's climate and weather. Dr Kepert is one of Australia's leading researchers in this field and is highly regarded internationally. He has authored and co-authored numerous research papers and reports and presents globally on fire and extreme or high-impact weather forecasting and the implications for communities and emergency services. At the end of the webinar, we will be providing links suggested further reading. The webinar will also be available on both the Bushfire CRC and AFAC websites, hopefully by the end of the week. Jeff will present for about 30 minutes today, or perhaps a little bit longer, and then you are welcome to ask questions by typing into the dialogue box, which is located at the bottom left of your screen. Our host today is Amy from Redback Conferencing, who is on hand to sort any technical issues or other concerns. Again, please use the dialogue box if you need. So now over to you, Jeff, and thank you for making time in your busy schedule for this webinar.
Okay, thanks very much, Sue, and thanks to Amy for the technical support and also to all of you for joining me. This is a bit of a new experience for me. I haven't done a webinar before. I'm used to a room of people, not a computer screen, so hopefully it will go all right. I'd like to acknowledge the members of my team who've worked on these projects, Robert Fawcett, Will Thurston and Kevin Torrey. And what I've decided to talk about today is, rather than go into depth on one aspect of the research, I'm giving more of an overview of some of the areas that we've been studying over the last couple of years. And I'm hoping it will give you an introduction to the sort of work we're doing and prompt you to dig a little deeper into some of the material. Most of what we're doing is using atmospheric models, and over the last few decades, atmospheric models have become very much more reliable and much more accurate and are a really good tool for understanding what the atmosphere is up to. The particular model we're using is called ACCESS, which is the Australian Community Climate Earth Simulation System, and it was actually developed by the UK Met Office, and it's one of the top international models. We've been using it operationally for a bit over 4 years now. I'd like to acknowledge my colleagues from the Earth System Modelling Program, led by Kamal Puri, who've implemented this for us. Typically, the simulations I show you, we start from a global simulation. So we simulate the entire world at coarse resolution, and we drill down, as you can see listed here, into finer and finer resolutions to resolve more and more accurately what's happening in the atmosphere. The finest resolutions they'll show today are on about a 400-metre grid, so that means we've divided the atmosphere up into little cells that are 400 metres by 400 metres, and that's the smallest thing we can resolve. So here's an example. This one's Black Saturday, and the simulation begins from the morning of Black Saturday. What you're seeing here is the colours are the surface air temperature and the little arrows are the wind direction, and you can see the wind change sweeping across Victoria. We'll loop back to the beginning of this now. So this is the morning. You can see the northerlies picking up in strength and then the very rapid heating as the sun comes up here. You can see the wind change progressing from the southwestern corner, coming through Melbourne and the Kinglake East fire at about 6 to 7 o'clock in the evening, and then as the temperatures cool, pushing into northern Victoria and the strong southerlies behind the change. There's a lot of detail going on in this simulation. You can see that the wind vectors ahead of the change have all got the jitters. They're flicking from side to side. We'll talk about that a bit more later. You can see there's a couple of major wind changes actually as we propagate in, and these very strong southerlies pushing in afterwards. These features sort of illustrate the complexity of the atmosphere and the power of the modelling in showing small-scale features that might be going on. I'll show you a few observations later that indicate that some of these things are actually real. But first of all, I'd like to sort of talk about wind changes a little. A lot of us are familiar with wind changes in southern Australia. We have a conceptual model that sort of says we have a northerly or northwesterly winds ahead of the change, which you can see up here, and then afterwards as the change pushes through we have southwesterlies behind. Of course, when the change impacts the fire, that's a critical moment for fire behaviour and for firefighter safety. We know that something over 95% of all deaths in Australian bushfires historically have occurred within an hour of the wind change. And prompted by that, the Bureau of Meteorology in some states produces forecast maps similar to these, which have got some of the have got the actual position at the time of issue. They've got forecast positions, and they've got arrows to indicate the wind direction ahead of and behind the change. These, of course, are quite a good and useful product. They give you a quick heads up of what's happening. But I'd like to caution you that they're actually a bit of a simplification of the rather complex situation we saw on the loop beforehand. One of the simplifications, of course, is that they can really only show a single line, and you might have spotted on the previous map that we had a couple of lines. Here's 6 o'clock, about when the change was passing through Melbourne, and I've marked in magenta, the thick magenta line, the major wind change, which was certainly the one that had a large impact on several of the fires on that day. But you'll notice that extending out to the west, there's this secondary change, which is not as strong as not as marked a wind gradient as the first one, but nevertheless there's a significant wind and temperature gradient over it. And if you have a closer look, there's actually a further small change extending down here, down to the Bellarine Peninsula and the Surf Coast. These smaller changes are too detailed to show on the large-scale map. It would just become a spaghetti of lines if we tried to put them all on. But in fact, they're still potentially significant for fires. So one of the things you need to remember about wind change maps is that, really like all the forecasts the Bureau issues, they're an attempt to communicate in a simple way a complex situation, and sometimes the simplification means that details that may be important have to be omitted. I'd like to have another look at that, the main wind change, and show you some cross-sections. These cross-sections are taken from a line that extends from about Cape Otway through to the north of Melbourne, through the Kilmore Gap and up towards northern Victoria past Yarrawonga. And the cross-section which actually moves along that line as the time goes by. So here's the cross-section. We've got distance along the line, height up to about 5 kilometres. The colours are showing you a altitude-corrected temperature. So the blue air is cool, the brown air is hot. It's potential temperature if you want the technical term, but for our purposes, altitude-adjusted temperature will do. And the black contours are showing upwards motion, the white contours are showing downwards motion. And you can see we've got the mass of cold air that's about 1 kilometre deep that's penetrated in at the moment we start the loop. So I'll now show you the loop. Obviously the atmosphere is a very dynamic beast. You can see the air really surging as it passes forward. And playing it again, you'll see that as we go through, there's a change in character of the change. It goes from being this mass of cold air, which is essentially being advected through, to later in the period, the cold air is occupying the surface of the Earth, and we've got more of a kink in the cold air. It's a little bit like a ripple in a rug that's propagating forward. Early in the period, the technical term is it's a density current. We've actually got new cold air that is flowing in to replace the hot air. But later on, as this cold air forms near the surface, and that's the nocturnal inversion, it actually becomes more like a wave rather than new air flowing in. The technical term is that it's an undular bore. And this undular bore accelerates and then propagates through. You'll see that some of the characteristics are still the same. We still have a strong updraft on the change itself, existing as we go through, but the cross-section is quite different. Well, how does this matter for fire behaviours? Is this talk of density currents and bores just meteorological jargon, or does it actually matter? Well, let's look at the next slide. The next slide shows us the 1-minute automatic weather station at Albury on the Victoria-New South Wales border, and the same time series from the model. So these lines up the top here are showing the wind direction, and they're pointing in the direction the wind is blowing. So these are northwesterlies here ahead of the change in both the observations and the model. The curves down here are showing the pressure observations, and circled we've got when the bore went through, and there's this little double hump in the pressure trace that's quite clearly visible, very characteristic of bore passages. But the wind directions are the really interesting bit. We can see we've got the northwesterlies before the change, and then it flicks around to the southwest. You can imagine the firefighters who were working the fire at the time would think, aha, we've got the change, it fits our conceptual model, the southwesterlies are in. They would have then been very surprised because it didn't follow the conceptual model. After about 8 minutes in the observations, it went back to northwesterly. This is something that's a bit characteristic of the bore-like change rather than the density current-like change, and it's something that our research has really highlighted, that these changes can exist in either form. They can change from bore-like to density current-like and vice versa. And we suspect this is the sort of information that could be quite valuable to firefighters. Obviously, it's not hard to imagine how the information that the wind is not going to stay southwesterly after the change, but is going to go back to the northwest, could actually be quite valuable to the folk on the ground who are working the fire. Here's another example. This is the Coonabarabran fire from January 2013 in inland New South Wales. The fire was actually at about the centre of these domains. And what you're seeing here is wind speed and direction on the left, air temperature in the middle, and the dew point temperature, which is a measure of humidity, on the right. So the warm temperatures are red in the middle, the warm temperatures are dry on the right. And here comes the major change pushing through from the southwest. But you can also see there's these cool patches of cool moist air forming ahead of the change. They're actually downdrafts from thunderstorms in the modelling, and our radar data, which I won't show you, indicated that the modelling captured those very well. The important thing with all these, if you look closely at the wind, there's actually a lot of complexity in the wind direction here. And if you look really closely, and perhaps it's a little bit hard to see in the loop, so on the next slide I've shown you just one snapshot, there's actually well and truly more than one wind change. So here we're looking at the temperature, dew point, and the wind vectors at about 6 o'clock in the evening, when the wind change, the main change shown by the thick magenta line, is about halfway through. But we have a secondary change to the southeast. This is cooler air of a coastal origin that's pushing in. Then we have this region of not quite so cool, but nevertheless cooler air, which is the large patch of thunderstorms, and you can see that their wind vectors are all over the place from the thunderstorm outflows. And then we have a number of smaller patches further to the north, where again we've got cool moist air and we've got significant fluctuations in the wind direction. From meteorologists' perspective, these wind changes are all different. They all have different causes. But from a fire perspective, in terms of what the fire sees on the ground, they're probably all fairly similar in impact on the fire behaviour. And we know actually from the very tragic deaths of 19 firefighters in the United States last year that who were caught when a wind change from a thunderstorm outdraft caught them, that the fire doesn't really care what the meteorological cause of the wind change is. As far as the fire is concerned, all wind changes are dangerous. And it's necessary to be cautious about the complexity of wind changes and the fact that there may be more than just the main change which the Bureau is forecasting. We're going to move on to a different topic now that's also been of interest to us, and that's the impact of topography on, or the interaction between topography, meteorology and the fires. These were fires that occurred down in Margaret River in southwestern Australia a few years back, and it was that rather difficult situation. It was a prescribed burn that escaped, so the intention had been to burn this area in green up near Ellensbrook, and there was also a secondary fire down here, prescribed burn down here, which I won't talk about. But the fire up near Ellensbrook had been, this was a springtime burn, late November. The fire had been quite reluctant to burn, and on the Tuesday night the fire crews felt confident that the fire was safe and actually departed. However, early on Wednesday morning, the fire escaped from this southwestern corner down here and subsequently burnt southwards. It destroyed some 33 houses, damaged some more, burnt through a major holiday area, and took 2 days to extinguish. So it was a major, really quite a major fire event. The interesting thing about the Margaret River fire was that it became active overnight. So on the Tuesday it had been very reluctant to burn, whereas between Tuesday night and Wednesday morning it became very active and escaped control bounds. And we were asked to have a look at this case and see what meteorological factors were important. The weather charts, just to give you a heads up, Margaret River is down where I'm pointing at the moment, right on the southwest corner. On the Monday we had gentle southeasterlies, tending a little bit more to the north on Tuesday, but still quite cool conditions. And on Wednesday we were seeing the shift to more northerly winds, and the temperature went from sort of the 20s to the 30s, and with the tightening of the pressure gradient, the wind strength increased. So it's no great surprise that on Wednesday, with those hot, gusty northerlies, once the fire had escaped, it kept going. But why did it escape on the Tuesday night? We had a look at modelling the situation at high resolution, and the fire, this is showing just the southwest corner of Western Australia, Cape Naturalist, Cape Lewin. The fire ground is shown by this little black outline in here. And these are the conditions at midnight on Tuesday. And you can see that the wind vectors are basically showing the east-southeasterly pushing through. The wind speed has become quite light over the land with the nocturnal cooling, except on this coastal fringe up here. The coastalmost few kilometres are actually quite windy. They're up around 6 metres a second, which is about 25 kilometres an hour, according to the modelling. We don't have any observations to confirm this narrow band of strong winds. The nearest automatic weather station is inland. But I'll show you later why we think this was happening, and we believe it's meteorologically plausible. Humidity conditions, the dew point temperature at this time is around 10 degrees, which is a relatively moist overnight conditions as you'd expect in the southeasterly stream. We push forward to 3 a.m, we see a couple of interesting things have happened. The first is that we've still got our coastal strip of strong winds, but it's actually freshened a little. It's up to 8 or 9 metres a second, which is about 30-35 kilometres an hour. and it shifted towards the northeast with the strengthening of the high and the bight. At the same time, the dew point temperatures have shown a dramatic drying. We've gone from 10 degrees down to around about 5 degrees. The origin of that drier air was that inland to the east of the Darling Scarp there was a massive continental dry air which, as the winds have shifted northeasterly, has been advected towards the coast. If we go forward another few hours until 8 a.m, this is about the time of the fire escape, we can see we've got our strengthening northeasterly winds, we've still got our dry air, so we've now had significantly drier air over the fireground for about 6 hours. And we've actually got further acceleration of the wind in the region of the fireground, this black outline. It's a little bit small on this map, but the strongest winds over land are actually occurring in the fireground, and that's associated with the topography, as I'll show you shortly. So with those strong winds, they're in excess of 10 metres a second according to the modelling, which is probably up around 40 kilometres per hour, and the dry air, that's probably sufficient to explain why the fire became active again overnight and why it pushed towards the southwestern corner and was intense enough at that stage to defeat the efforts of the fire crews who arrived back at about this time and engaged the fire but were unable to stop it from breaking out and heading further south. Here's a loop which starts at 6 o'clock on the Tuesday night. You can see the strip of strong winds right down the coast, various small changes moving through. Then the winds are shifting northeasterly, strengthening further. We have the strongest winds persistently in the coastal fringe and now accelerating towards the morning over the fireground. A couple of other interesting things we see. There's these lines of stronger winds that are sweeping across from west to east. They're topographic streamers which are being shed from a large hill up here near Cape Naturalist, just south of Cape Naturalist. They're not the sort of feature we have a lot of evidence for occurring in the atmosphere. They're very hard to capture in the observations, although very apparent in modelling. But I was interested when I flew down to Hobart a few weeks back, and there was a lot of smoke from the Victorian fires around, that you could see the signature of these streamers extending across Bass Strait from the topography. The smoke made them very easy to visualise. So why did we get the strong winds on the topography? Well, here are two cross-sections. They're aligned with the wind direction. Each one is 50 kilometres long, and they go straight through the fireground. So the fireground is at the middle. 4 a.m. and 8 a.m. And we're seeing three fields. The first one, which is labelled with the Greek theta, is the density or the altitude adjusted temperature. You can see at 4 a.m. we've got very closely spaced contours, strong nocturnal stabilisation. The next one is the vertical velocity, and you can see there is this enormously strong downdraft in the lee of the hill, and this hill was basically the fireground. And the third one is the horizontal wind speed, and you can see there's this marked low-level jet of about 20 metres a second, which translates to about 75 kilometres per hour. That's very close to the surface. So what we're seeing here is a little bit like what you see when you have a rock in a stream. And you know that when you have a rock in a stream and the flow over the rock, the water tends to bank up on the upflow side and accelerate very strongly down the downflow side. You get this thin layer of very fast-moving water. This cool air near the surface essentially gives you much the same effect. You get this very strong acceleration and a thinning out of the flow. You can see the contours are closer together on the downslope side, the downwind side of the hill, than on the upwind side. And that leads to a marked accelerating downslope flow, and the surface winds, according to the modelling here, as I said, we're getting up towards 40 kilometres an hour. This is at a time of day when we normally expect the winds to drop off, of course, so it's in conjunction with the dry air was probably enough to sustain the fire and indeed intensify it from what it had been the previous afternoon, and push it out across the control line and into the unburnt fuels to the south, where it, from then it was basically unstoppable. Of course, sometimes we get both topographic effects and wind changes, and just to give you an idea of the level of detail, this was the Dunalley fire from also from January 2013. We have air temperature on the left and wind direction on the right. So the hot colours are northerlies, and the green and yellow shadings are the southwesterly behind the change. You can see the strong heating over the fire ground. That was a fern wind effect. And then here comes the wind change, and you can see this large area of green and yellow pushing through. Embedded in that, sorry, I'll wait for it to go back again. Here's the heating due to the fern effect on the downslope off the Tasmanian Central Highlands. And then here comes the wind change in the blue and green. You can see embedded in it, there are these patches of blue, which is actually a northeasterly direction. When I first saw these, I thought, the model is really playing us false and doing some unrealistic stuff. But we had a look at the Maria Island, which is one of the islands off the east coast of Tasmania. You can see the northerlies. This is a plot of wind direction against time. The northerlies ahead of the change through here. And here's the wind change, but it's actually gone easterly. And sort of illustrates the complex effects you can get when you have both topography and the wind change together. But it also illustrates the skill of the model in that it predicted this. The other thing we saw in the Black Saturday simulation that we'll go back to now is there was this region, and in the northerlies ahead of the change, where we saw the wind vectors were jittering. They were flicking from side to side. And I now want to have a look at that phenomenon in a little bit more detail. Here's some cross-sections. So this is up in the centre of that region, and what we've plotted here, get my laser pointer back, what we've plotted here on the right, these are the surface streamlines, so the direction of the surface flow, and then we've got the vertical velocity at about 1 kilometre height. And you can see there are these confluence lines where the streamlines are flowing into these long, thin bands of updraft. And they're very organised updrafts, aligned basically with the mean wind. This black line here shows a cross-section line, and you can see here we've got, again, the colours are showing vertical velocity. We've got these organised, coherent up and down drafts alternating through the flow. If you imagine what this would look like, imagine you're standing with your back to the wind, and what you're basically seeing is successive pairs of counter-rotating vortices in which we've got superimposed on the mean wind, which is flowing into the page, we've got these pairs of counter-rotating vortices. And what you're seeing here is the updraft between two vortices and the downdraft between two vortices. So this was at 1 o'clock in the afternoon local time. If we go forward an hour, we see that the lines have become a little bit less regular. They've become rather stronger. The updrafts are now up to about 5 or 6 metres a second, which is a significant updraft. That's enough to suspend firebrands, and they've become a bit broader. And if we go forward another couple of hours, the rolls have broken up further. They've become more irregular, and they've also become stronger in terms of the updraft strength. My colleague Will Thurston had a look at the characteristics of these, and over that aerial domain I've just shown you, he plotted the variation in the surface wind direction. So basically the frequency distribution of the variation in surface wind direction. Normally when you plot frequency distributions, you'd expect something like a Gaussian a bell-shaped curve. But what we've got here is actually something that's quite flat with a couple of little bumps at the edges. And you can see most of the winds are a plus or minus 20 degrees of the mean wind direction. If we plot these, if we take a whole bunch of similar curves at different times and put time up the axis and plot the density function of the wind direction variability, we find that about 1:30 in the afternoon there was this sudden explosion, broadening of the direction variability. And that occurred with the onset of the rolls. Potentially quite significant to fire behaviour, because we're seeing these rolls migrate sideways with time. And so if you were standing on the ground, about every 20 minutes you'd see the wind direction swing by about 40 degrees. And that's enough to give the flank of a fire some head fire characteristics or some backing fire characteristics. And is potentially the sort of thing that could be quite important to fire behaviour, especially if you're a fire crew on the flank of the fire. These things are not just a figment of the model's imagination. Here's some imagery, and we'll just look at the right-hand panel. This is the reflectivity from the weather radar up at Yarrawonga. What we're seeing here is actually a reflection from insects, but you can see that there is a tendency for those for the reflectivity to be organised into parallel lines, and that is because the insects get drawn into the updrafts and are then lifted to a height where the radar can see them. We also had satellite data that indicated that these things were real. And if we look at the weather observations again from Yarrawonga, we can see that somewhere around about here, at about 1 in the afternoon, the temperature fluctuations suddenly increase in magnitude. And sort of after this time, we've got an increase in the wind direction fluctuations. They're gone from being, say, plus or minus 20 degrees to about plus or minus 60 degrees. There's something of an increase in the speed fluctuations, and there's also a marked increase in the temperature fluctuations, all of which are characteristic of the rolls. The last little thing I'd like to look at is quite a different topic. This is even higher resolution simulation, and we're trying to understand, this is a bit of research which we've only just got going on and is fairly new, hasn't yielded as many results as the other, but we're trying to understand Ember transport, having got interested in it by the reports on Black Saturday that spot fires were lit up to 34 kilometres ahead of the main fire. So we're trying to understand how bushfire plumes can transport embers, firebrands, and more importantly, we're trying to predict how far, or trying to develop methods to predict how far they can be transported on a given day. And is today going to be a bad day for ember transport? To do this, we're using what's called a large eddy model, which is a very high resolution model, 50-metre resolution. And this just gives you a snapshot from the large eddy model of the atmospheric turbulence. So we have an atmospheric boundary layer that's about 2 kilometres deep, and here are the fluctuations in the along stream, cross stream, and vertical velocity. What we then do is we take these simulations and we put a plume in, which we model by a surface heat source. So you can see, and the colour scale's changed here to emphasise the plume. This is showing the strength of the updraft. Brown colours are up. You can see here's the plume. The background wind here is 15 metres a second, which is about Black Saturday-like conditions. That's a little under 60 kilometres an hour. And you can see the plume is quite bent over in the influence of the strong winds and weakens as you go downstream. It weakens because it mixes with the surrounding air, and therefore the temperature perturbation in the plume becomes weaker. If we look at an animation of that plume, you can see how unsteady it is. Now, this unsteadiness is not produced by the simulated fire burning through different fuels. The simulated fire is actually completely constant in time. There's no, it's producing a certain heat flux, and that heat flux is fixed because we're simplifying the situation. But you can see that the plume, like real plumes, is meandering and is puffy. There are puffs that go up and persist for a length of time. Here's another view of the plume. This is showing not the vertical velocity, but essentially the smoke density in the plume. And again, you can see the meandering, unsteady characteristics of it, and also that as it mixes with the surrounding air, the smoke becomes diluted until it gets below the threshold at which we've chosen to plot it. Where this gets really interesting is when we consider the ember transport problem. So in the plume itself, we drop a large number of firebrands or embers. These have a fall velocity. We've used 6 metres a second, which is based on work by Peter Ellis and Andrew Sullivan in their vertical wind tunnel. And what you can see in the next simulation is the embers being transported by the plume and falling out. There are some interesting features. The first one is how far they go. In this particular plume, which was characteristic of a large fire on a windy day, we're quite easily getting embers to travel to about 15 kilometres downwind of the source. The other thing is that the plume basically drops a fairly continuous stream of embers all the distance out there. Most of them fall relatively shorter distances. But you can see also the impact of the unsteadiness of the plume on the embers. There are periods where the plume is strong and periods when it's weak and drops a large cluster of embers in the one spot. There it goes doing that now. So there's still a long way to go with this research, but we are hoping that at the end of the day we're going to be able to have a sound physical basis for saying that this particular fire, given the particular meteorological conditions, is going to have the following spotting characteristics. And by being able to predict where the embers are landing, we're actually going to be able to help the firefighters and the fire agencies to better manage the threat from spotting when they're dealing with a fire. So that's a bit of the snapshot of our research. I hope you found it interesting. I hope it encourages you to perhaps look a little bit more deeply at some of the things we've been doing. And we've certainly had a number of reports and publications that have come out that we'll be directing you towards. I'd like to just talk a little bit about where this is taking us in the future. As computer power gets bigger and better, we're going to, in the Bureau of Meteorology, we're going to be moving from these sort of resolutions being the sort of things that we can afford in research mode to the sort of things we can afford every day. 400 metres resolution is probably 10 years or so away, but the higher resolutions that are starting to resolve some of these features are only a short year or two away from being operational. So we are going to be better able to capture the fine scales that affect the fires. One of the initiatives that we're hoping to take in the next few years is to run a special severe weather version of ACCESS. Australia is a challenging place to forecast for because it's so big, and the computer power to run high resolution over the whole of Australia is not going to be available for a long time. But if we can do a run-on-demand high-resolution version and put the resolution where the weather is, we're going to have the capability to actually show some of these, to predict some of these very small-scale important features in real time. The challenge is going to be how do we use this information. For example, wind changes, they're not all the same. Sometimes they're bore-like, sometimes they're density current-like. Sometimes there's lots of changes, as we saw on Black Saturday and even more strongly at Coonabarabran. They're of crucial importance for the fire services, but in the face of this enormous complexity, how do we communicate that information? The other direction that we're hoping to take ourselves in the next few years is what we're slightly tongue-in-cheek calling a SWAT, which is a severe weather analysis team. We think the work we've done the last couple of years with post-event analysis of fire events has been very important, and we've also, other folk in my team have done similar post-event analyses for tropical cyclone cases. So it's very important in the emergency services management game to learn lessons, because the natural world continues to throw new twists on old disasters at us, and we have to be forever learning to cope with these things and to not fall into the same situation again, to make sure that the next time we're confronted by one of these situations, we cope with it much better. I think it's probably fair to say with the severe fire danger we saw in Victoria recently that we coped with that much better than we did on Black Saturday. But it's important to continue to learn lessons, and part of that is to continue to have a good hard look at the bad events and find out what we could have done better. So that's it from me. A little bit longer than I meant to be. Sorry about that, and I'll welcome any questions now. Thank you. Okay, I've just realised I have a question from Sue. I should have said I think you can use your microphone for your questions, but you can also type them into the box down the left-hand corner of your browser.
Yeah. And my question, Jeff, I've always been in awe of Mother Nature, and now I think I'm in awe of the technology that's behind being able to predict and model some of what the huge variability and complexity behind this. What's been the uptake or the ability of being able to inform the fire services on this today?
Some of it, Sue, has been a question of, or a matter of just raising awareness. I know when we've talked about roles and systematic variation in wind direction, we've had people come up and say, you know, we've seen this sort of thing on the ground, and we've seen the fire run one way, then run the other, and then run the first way again. We've never really known how to do that, and we've never really known what's causing it, or what's causing those, you know, large temporary changes in wind direction. So partly it's important just from a raising awareness point of view. One of the areas we'd like to take the research with the roles in the future is to actually look at whether it's possible to predict that, you know, today is going to be a bad rolls day. So you might expect strong lateral I'll start again. You might expect strong lateral spread of the fire because the wind is going to have a large amount of direction variability. At the moment, that is still work that's to be done, but you know, it's the transition to operations is always a little slow. Another one that I think is important in terms of awareness raising is just the fact that you get different forms of wind changes, and you know, when the wind change on Black Saturday went through the fire in northern Victoria, up near Beechworth, it produced a major outbreak of spotting, and the firefighters had a difficult time in managing it, and that happened at about midnight. Again, it's not the time of day when you're expecting things to get bad. I think potentially that's something that in the future the Bureau would be able to help with forecasting, because we now understand the processes that are going on in the atmosphere quite well, and I think we've probably got the capacity to look at being able to predict the difference between bore-like changes and density current-like changes, although we probably want some simpler words for that than that for the firefighters. Rob S. is asking me, how do I think this can assist with spread modelling? It's a good question. This work, and I probably should have said this at the start, was actually part of a larger project, the FIRE-DST project, of which you've probably heard, which was a collaboration with Geoscience Australia, Melbourne Uni and CSIRO. One of the things that was done as part of that project was to take this time-varying and spatially rich weather data and run Phoenix on it. And we found a number of interesting differences compared to running Phoenix off just a single point source of wind. For example, the wind change doesn't hit the whole fire at once. It usually hits, in the case of the Kilmore East fire, it hit the southern end of the fire before it got to the north. And so that had an impact. That led to a different spread prediction. We also found that there were some differences in the predictions depending on how coarse a resolution we fed the wind in at, and we put some effort into trying to decide whether these differences were, or trying to use this research to decide what was the best frequency with which to feed Phoenix. Noreen is asking me whether I have any tips for people on the ground about how to identify these different types of wind change. That's another good question. Physically, what causes the wind change to be density current-like or bore-like really depends on the difference between the surface temperature and the air temperature. If the surface is hotter than the air, you'll tend to get a density current-like change. If it's significantly colder, you'll tend to get a bore-like change. We actually often see bore-like changes over the ocean because you've got cool marine air, and the cases we've seen where the bore changes into a density current have been when you have a wind change propagating from the ocean over the land. So I'd hesitate to say that it's a hard and fast rule at present, Noreen. We haven't had a look at a large enough number of cases, but based on our knowledge of how the atmosphere works and what we're seeing in the model, I'd say as a rule of thumb, if you've got relatively cool land, so either the ocean or the relatively cool surface, so either the ocean or the land at night, it's probably more likely to be bore-like. And if you've got hot land, so during the day, then it's more likely to be density current-like. John is asking how much lead time do we need to run the model? How large an area can it cope with, and what happens when we have significant topography changes? To run these simulations down to 400 metres, when we started doing them, the first one took Robert Fawcett, who does this work. They were taking roughly a week to perform the calculation. So obviously that's not something you can do in real time. Just in the last few months, we've moved them from running on our own supercomputer to running on the national computer infrastructure up at Australian National University, and they now take him a day. So that's still not something we can do in real time, but it's certainly getting closer. at that resolution, we're running on a domain that's about 300 to 400 kilometres square, and that's actually a resolution where we're capturing most of the significant topography changes. We still have to apply some smoothing to the topography to get it to that resolution, but we're actually capturing most of it. To give you an idea, I think the hill in the Margaret River simulation, in the model that's 180 metres high, and in reality it's about 200 metres high. So we're certainly capturing the majority of the topography. Nicholas is asking me about wind change maps, and says, as you mentioned, these do not reflect the complexities. Are there any thoughts around updating the wind change maps produced to reflect the complexities, or how should operational staff take into account the complexities of wind changes when managing a fire on a day of heightened fire danger? That's another excellent question, and it's something that we've had a lot of internal debate about. There are, I think it's probably fair to say that there's a significant body of thought within the Bureau that says that, well, you know, it's a good product for a quick heads up, but we're quite uneasy with the fact that we have to simplify the complex situation so dramatically in order to reduce it to simply a line on the map. At the same time, we're aware that there's a push, you know, that users like simple, direct, clean communication, and that graphical product is actually very clear and very simple and easy to understand. And so we've got a tension between oversimplifying, but at the same time providing the users with information that they can assimilate. I have had people in the emergency services tell me they don't want to know about, you know, this complexity is all very well, but all they want is a line on the map. I think we're probably getting to the point of knowledge where our knowledge is and our ability to predict is such that the line on the map is going to have to be superseded. But at this stage, it's not terribly obvious as to how we would supersede it. The current product is beautifully clear and beautifully direct, but it's an oversimplification. I think perhaps the best way to manage it in some states is where they have the fire weather forecaster posted to the control centre, and they can actually pick his or her brains and ask them in detail. It may be that a simple graphical product that captures all that complexity is not possible. On the other hand, it might be that something clever could be done with an animated graphical product on a smartphone or tablet. So it's perhaps not a satisfactory answer because I don't think we've yet got the answer, but it's certainly something we're talking about. Are there any further questions? I think I might hand back to Sue in that case.
Yes, this has been so fascinating, particularly for someone who's a very lay person like myself. And I really thank you for your time in presenting what's pretty leading edge research in this area. And, you know, I guess bring it on and whatever we can do to get this type of data and information into the you know, our people on the ground and our planners, the better. So thank you for your time today. Please remember, everyone, that this webinar will be available on both the Bushfire CRC and the AFAC websites. It takes a couple of days. We'll hopefully have it up by Friday. If not, it will certainly be there by Monday. And I think that we've got a lot of folks saying it's been very useful, and thanks for your time there, Jeff. There will be a little exit survey as people leave this webinar, and we really would appreciate your feedback. There are some upcoming webinars. Dr Andrew Edwards will be discussing mapping fire severity and assessing carbon and greenhouse gas emissions in the tropical savanna in Northern Australia. That's on Wednesday the 2nd of April. And I've just had confirmation through that later in March, either the 26th or the 27th, Chris Weston and his colleague Luba from Melbourne University will also be presenting a webinar. So please look out for those invitations, which will be coming out soon. Again, Jeff, thank you for your time today. It's been, I'm sure, very interesting for a lot of the people who've attended the webinar. We hope you'll all join us in future for future events. Thank you.
Okay, and thank you all for attending and for your interest. And thanks also for the feedback at the end. I couldn't see your faces during the talk, so I didn't know if you were all asleep or not. It's nice to see you typing something in at the end, so thanks for that. Thanks to Sue and Amy and Noreen for their work in organising it also, for the opportunity.
Wonderful, thank you.